The next thing we're going to talk about is dropout, and that has been described as an approach to making bagging practical for ensembles of very many large neural networks. So keep in mind all this information we talked about previously about ensembles, because this is quite relevant to dropout. And dropout is as this quote here shows, quite relevant for deep learning, especially. So where does the name come from? Well, it comes from the fact that we are going to be randomly dropping input or hidden nodes during training. So during training, we will drop them in the sense of just ignoring them, setting them to 0. And in general, at the high level, this is equivalent to ensembling all networks with a subset of units missing. So just to illustrate this, we have this simple network here with 2 inputs, 2 hidden units, and an output. And so if we delete some subset of these from the network, we will end up with these subnetworks, which are illustrated on the right. And so you will see some of them are kind of useless networks with no connections, but some of them are still we can get from the input to the output, and by ensembling those, we could. That's what dropout would do if we apply dropout to this. It will implicitly ensemble all these networks during training. And so let's first take a look at what happens when we training a network using dropout. So for each input, we sample a binary variable, so a variable which takes the value 0 or 1 from a Bernoulli distribution with probability p input. And then we will multiply unit activation with the sampled variable. And so in simple language, this simply means that we will randomly set some of the inputs to 0. We will just ignore some of the inputs. And likewise, for each hidden unit, we will sample a binary variable from a Bernoulli distribution with a different probability p hidden, and then again multiply unit activation with a sampled variable for this particular hidden unit, and that again has the effect of randomly ignoring some of the hidden units, just zeroing them out. So this set of sampled variables is called a dropout mask. So a mask is simply a random vector, binary random vector, which can be multiplied with activation vector to simply zero out some of the units by doing element-wise multiply. And so once we have trained the network using this approach, we will then also need to adjust the way that we apply the network on new inputs. So doing testing, also called inference. And so what we will do, we will multiply the outgoing weight of each unit by the probability of keeping this unit that we were using. So p hidden. Or p input, depending on the unit that we're talking about, and this has the effect of maintaining the expected total input to a unit at test time, similar to the expected total input to that unit at train time, when some of the weights, some of the units were missing at train time randomly. So we will just do this adjustment in order so that there is no mismatch between how the values that the network sees during training and testing. Okay, and so this Hinton et al. In 2012 showed that this is approximately means taking the geometric mean of the output of all subnetworks. So in that sense, that is doing the ensembling. It's just this geometric averaging. And so one question is, why would you want to do it like this? What is the difference between dropout and explicit bagging? Maybe we can just explicitly train a few thousand different subnetworks and then just ensemble them explicitly rather than doing this dropout trick. So why do you think one is better than the other? Why would we prefer to do the dropout? Well, I suppose the answer is relatively obvious. It has to do with the fact that if we have to train a few thousand networks and our networks are very large deep learning models, that becomes prohibitively expensive. Whereas with dropout, we're just reusing the same network just for each for at each point we simply apply some random mask, and thus we are changing all the time which subnetwork we are using. So we only need like a single network, single explicit network, but which includes all these subnetworks via this dropout operation. So that's the reason we do that instead of explicit bagging. So Hinton et al. This 2012 paper make a connection between dropout and sexual reproduction from biology, and so this is an interesting connection that I wanted to briefly mention. In biology, sexual reproduction involves randomly swapping genes from two parent organisms. So this happens during chromosomal crossover during meiosis, and so the effect this has is that it prevents co-adaptation in the sense that genes need to be able to work with different versions of other genes, of different alleles of other genes, because at each generation they could end up being in the genome with other versions, and so they have to be such that they will not break. They will still be able to function in a reasonable way. So that's what meant by preventing co-adaptation. The genes are somehow can work are robust to changing to the changing genetic environment that they are in. And so Hinton et al. Claimed that this is dropout has a similar effect in the sense in neural networks, in the sense that there is no reproduction here, but simply that it encourages modular representations, or that the weights of the values the weights of the network are such that if we slightly change or remove some parts of the network, they still will work. So the network is going to be less fragile. It's going to be more robust to changes, and that also makes it in practice makes it generalize better to unseen data. So standard dropout that I described so far, that works well with feed-forward architectures, including convolutional architectures. However, it's been shown that for recurrent networks, which we will discuss in a future lecture, it needs to be adapted, because there is this notion of recurrence in a recurrent neural network. There is some particular way of sharing weights, and so regular dropout doesn't really work very well in that case, and we need to adapt it by keeping the mask the same for each time step in the recurrence. So I will not go into the details now because we haven't seen recurrent networks yet, but just keep in mind that dropout needs to be done in a specific way for these recurrent architectures. So one more thing I wanted to mention is adversarial training. And so first of all, we might want to look at adversarial examples. So these adversarial examples are cases where the way that we perceive things as humans and the way that a system deals with them is very different. So what you see here, this is an example from the paper which introduced the concept of adversarial examples, and you have some pictures in the left column. Then there is some specific pattern added to that picture. That pattern is a bit amplified here so that we can perceive it, but basically it kind of looks like just noise to us. If we add this pattern to the picture on the left, we get the picture on the right, which to us as humans looks pretty much the same, almost exactly the same. And we will definitely not perceive these objects as being different. So the first one would be a truck, and the second one would be some type of bird, and so on. Whereas for this particular noise patterns that are added to the picture change the labeling that a neural network, that a convolutional neural network trained in a standard way output. So instead of saying truck in the first case, I don't remember what the change label was, but maybe it will say kangaroo or something. So it will just completely change the output of the network, even though for us it looks exactly like the original truck. So this is called adversarial examples. And so what is meant by adversarial training? Well, so let's have a look a little bit at a very simplified formal example of why these adversarial cases would even be possible in the first place. So the output of a linear function, such as this one, with the weights or coefficients w, input vector x, and some bias b, the output can change by a large amount if each of these inputs x, so each dimension in this input vector, is changed by a small amount, as long as w has many dimensions. So the reason for this is that that if x and w are large dimensional and we change each x by a small amount, if we sum all these small amounts together, that can amount to a large value in the end, and it can change the output value by a large number. So so that is in this sense, linear functions are sensitive to local perturbations. We can make small changes to all these inputs, and then the output is going to change. The change to the output is going to be large. And so adversarial training is something that we can do to prevent neural nets from exhibiting such linear behavior. And what adversarial training does is simply, if we go back to these pictures, we will just first of all make such adversarial examples, and these are done by simply optimizing these patterns that we add into the images such that they maximize the error of the model that we are using to do the labeling. So we will generate such adversarial examples, and we will just add them to the training data, and we'll train the model or retrain the model again, and so, but without actually changing the labels, right? So we will have the original truck and the truck with the adversarial truck, which originally the model thought would be a kangaroo or something, and we will add many such examples to the training data of the model and retrain it, and then the model after this retraining will hopefully be less sensitive to these local perturbations and will generalize better to unseen data. So to summarize what we've seen in this lecture about regularization, is there are many different ways of or many different things that can be called regularization, or that have aspects of regularization to them. We have seen several of them. I want you to especially pay attention to two of them: early stopping and dropout. These are things which are basically obligatory in deep learning. We always do these things, almost always. They are very standard. The other approaches to regularization are also interesting. They're not always used. They are not universally used, but definitely something to consider. Dataset augmentation is also something that is especially pretty standard in vision and especially in object recognition. It's pretty well understood which of these work and how, and so it's by now it's also the standard part of the toolkit. So keep this in mind.